Welcome back, students. We were discussing about the partial differential equations in the last lecture, where we have seen the elliptical PDE, parabolic and hyperbolic PDE, and we also saw in the last class the some of the concepts of the finite differences. So, we are going to proceed forward now and talk about elementary finite difference quotients. So, derived from Taylor series expansions. So, the elementary finite difference quotients are derived from the Taylor series expansions. So, example is that uij is the x component of velocity ui plus 1 at point I plus 1 comma j can be expressed. So, you see uij is the x component of the velocity, okay. ui plus 1 comma j at a point I plus 1 comma j can be expressed in terms of Taylor series expansion about point I comma j as. So, ui plus 1 comma j can be written as ui comma j plus delta u del x at I comma j into delta x plus del square u by del x square at I comma j multiplied by delta x square by 2 and so on. So, this is using Taylor series expansion. All right. So, this actually can be truncated after finite number of terms. I mean, we can decide 3 terms or 4 terms or 5 terms. So, we have decided to truncate it after 3 terms. So, ui plus 1 comma j can be written as ui comma j plus del u del x multiplied by delta x del square u del x square into delta x square by 2, and these are evaluated at I comma j, both of these terms. So, this equation is second order accurate because we have a square term del square u by del x square. So, if you want to make it first order accurate, it can be written as ui plus 1 comma j is ui comma j plus del u del x evaluated at I comma j into delta x. So, this is first in first order, so it is first order accurate. So, it is now obvious that the truncation error can be reduced by retaining more term in the Taylor series expansion of the corresponding derivative and reducing the magnitude of delta x. So, one important thing to note here is that there is a truncation error, right. So, the full value will be the exact and perfect value, but we have decided to truncate some of those terms. Truncate means leave out those terms, correct. So, this error can be reduced by retaining, first way is retaining more terms in the Taylor series expansion, right. The more the number of terms, the less will be the error. And if we reduce the magnitude of delta x, then also that can be there, right, because this delta x is reduced, then delta x square x cube will be even more and more less. Therefore, the truncation of those terms we do will be almost negligible. So, from the above equation, you see the first order equation and the second order equation, if we write, we can evaluate del u del x at I comma j, which means del u of I plus 1 comma j minus u of I j divided by delta x plus truncation error, whatever we have left out, okay. So, this is actually called the first order forward difference. Forward because we have I plus 1. So, if say this is I comma j and this is I plus 1, this is I plus 1 line and this is j line, this is j minus 1 and this is j plus 1, and then that means it is forward I plus 1. Similarly, we can also write del u del x I comma j in the backward direction. That means u I comma j minus u I minus 1 comma j by delta x plus whatever the truncation error is, and this is called the first order backward difference. So now you understand the difference between first order forward and first order backward difference. So in the forward we have I plus 1 minus I, and in the backward we have I minus I minus 1. So I indicates the indices at the grids, alright, of the grids. There can be another way where you can actually, so let us say this is I minus 1, this is I plus 1. So you can just do this one dead. Okay. So first write the equation between these 2 points, then write between these 2 points and subtract. This is what we have done here, So this actually gives the difference between ui plus 1 minus ui minus 1, you see, and then it will be divided by 2 delta x, because the length between this is delta x and this is delta x. So this total becomes 2 delta x. So this is another way, and this is called the second order central difference, because we are calculating, what were we calculating? Again drawing, this is I comma j, this is I plus 1 comma I minus 1 comma j, this is I plus 1 comma j. So we are actually calculating del y by I minus 1 I plus 1. So we are actually calculating del y by del x at point I comma j. So it is that therefore we are calculating the value of dy by dx here using the point back here and here. That is why it is called the second order central difference. This is central. In the backward, you see, we are calculating at I using the one there minus the one at the back. Here we are calculating at I using the one in front minus the current one. All right. So we have to put time derivative as forward difference and space derivative as central difference. Okay. They called the FTCS, forward time central space. So what we do, we have to put time derivative as forward difference. So time as forward difference, because time cannot be in the back. So we will always have to be forward, and for the space we use central difference. That is the most standard practice, and this is called as FTCS, forward time central space. Alright, so you are expected to know these terminologies, what FTCS is, what is forward difference, what is backward difference, what is central difference, for time derivative which is used, for space which is most commonly used. So for space we said that it was a central difference, for time it is the forward difference. So terms like that are quite important. So we write ui in this is for the time, you see this n. So we write ui n plus 1 minus ui n is alpha ui plus 1 n. So these I plus 1 and I minus 1 are all calculated at the previous time or at the current time. Okay. Suppose we are at, let's say we are at time t is equal to 1 seconds, we have the solutions, we want to calculate for t is equal to 2. So velocity at t, this is at t is equal to 1 second, this is also the, yes, okay, this is also at t is equal to 1. So you see n. So these all things we know from the previous time step. What we need to know is ui at n plus 1. So there is a term called consistency now. So what actually is consistency? So a finite difference representation of a partial differential equation is said to be consistent if we can show that the difference between the PD and its finite difference representation vanishes as mesh is refined. So this in a different word, if this representation of a, I mean, see, we said that we are going to represent partial differential equation in an algebraic form, correct? So this algebraic form is currently finite difference method, right? We are using the method of finite difference to represent it into algebraic form. So this solution is consistent if we are able to show that the real solution, that is the PDE solution, the difference of that with the one that is obtained using the current method, that is a finite difference method, will go away, will be 0, or it starts to go to 0 as we have gone delta x is refined, as mesh is refined, as mesh goes to 0. Alright, as the mesh is refined. This is the, you remember we had this limit delta x goes to 0 in your limit analysis. So limit of mesh goes to 0, the partial differential equation minus the finite difference equation goes to 0 if the mesh size goes to 0. If we are able to show that, that means our solution of the partial differential equation using the finite difference representation is consistent. There is another term called convergence. So the solution of the algebraic equation that approximate a partial differential equation, same thing, okay, is convergent if it approaches the exact solution of the PDE for each value of the independent variable as grid spacing tends to 0. Okay. So the solution of this, this solution is said to be convergent if this solution approaches exact solution of the PDE for each value of the independent variable as the grid spacing tends to 0, not the combination of different variables. If for each an individual, for each x and y, for example x and y are the independent variables, or for each of these x and y this should converge to the real original solution of the PDE, then that means the solution is convergent. So the requirement is ui at n is equal to u bar xi comma yn as delta x delta t goes to 0. Alright, where u bar xi yn is the solution of the system of algebraic equations. Now there is something called the error and the stability analysis. The numerical solution which we have obtained using the finite difference scheme, they are influenced by two sources of error. One is the discretization. The errors are introduced due to two methods, one of which is discretization. This is the difference between the exact solution of the partial differential equation and exact solution of the corresponding finite difference equation. Alright, truncation errors. Second, there is round off error. So this is a numerical error introduced for a repetitive number of calculations in which the computer is constantly rounding the number to some decimal point. Suppose the accuracy of the computer is, let's say, 3 decimal units, okay, and if our solution is 1.117985, or let's say assume the value of pi pi is 3.14 and it goes on, right? So when the computer is, let's say, third accurate up to third order, the computer will keep on rounding the values. Therefore there will be one error introduced due to the rounding off. So one due to discretization, second is due to the rounding off. All right. So this are the two errors that we had talked about. Now we can proceed to another concept in the computational fluid dynamics module, that is von Neumann stability analysis. So what is this stability analysis? We say if A is the analytical solution of a partial difference accuracy and D is the exact solution from a real computer with finite accuracy. Okay. So A is the analytical solution of partial difference accuracy and D is the exact solution from a real computer with finite accuracy, and N is the numerical simulation from a real computer with finite accuracy. Okay. So A is analytical solution, D is exact solution, exact means perfect solution, and N is the numerical simulation. If we use these three terms, okay, then the discretization error is A minus D is equal to truncation error is equal to the error introduced due to treatment of boundary condition, whereas the round off error epsilon is N minus D. Now you understand these round off error and the discretization error. Discretization error is A minus D. Okay. So discretization A minus D. So the difference of the analytical solution of the partial difference accuracy minus exact solution from a real computer with finite accuracy, whereas the round off error is N minus D. Alright, so this is von Neumann stability analysis, and we can write N is equal to D plus E, D plus epsilon. So the numerical solution N must satisfy the finite difference equation like this. Alright. And D is the exact solution of the finite difference equation, hence it exactly satisfies this one, A and B. Right, A was the finite difference in the first page that we saw, A, you see this is A, D is the exact solution of the finite difference equation, and it exactly satisfies this. So N will satisfy both. So if we perform A minus B, so epsilon of N plus 1 minus epsilon I of N delta T will be written. So from this equation we can see that the error also satisfies the difference equation. For stability, the errors must shrink from step N to N plus 1. So the mandatory condition is epsilon I of N plus 1 divided by epsilon of I at time N must be less than 1, because it is supposed to decrease. If assume that the distribution of errors along the x axis is given by a Fourier series in x and the time wise distribution is exponential in t, then we can write epsilon x comma t is e to the power a t. So this is the equation using which it is given. Alright, L is the unit complex number, alright, or I, capital I, and K is the wave number. This is very complex. Since the behavior of each term of series is same as the series itself, hence let us deal with just one term of the series and write. So we deal, see there are lot of term in this series, right? E, A, T is the sum of E, I, K, M, X. So we just use only one term, and we write E of M x comma T is e to the power A T, e to the power I, K, M, X. and if we substitute this equation in the error equation, you see that error equation that we had got, this was the error equation, and if we substitute this in the error equation, we are going to get a complex equation like this. All right. Now if we divide this equation by e to the power at e to the power I km of x, we are going to get, on the left hand side, we are going to get e to the power a delta t, because t and t will get cancelled, is equal to a more simplified solution, e to the power I km delta x, because x and x plus delta x, so this will remain delta x, here also delta x. All right, and yeah, this will completely go away, this will, you know, all right. So on dividing by e to the power alpha t at e to the power I km of x, we can therefore write, using this equation from here, we can write e to the power a alpha t can be written as 1 plus alpha 2 delta t plus divided by delta x square. So you see this term here, okay, or we can write it in terms also of sine square by 2 term. So it becomes 1 minus 4 alpha delta t by delta x square sine square km delta x by 2. The derivation is not in your scope, but we will finally look at the answer, the result that we are going to get. Therefore we can write this e to the power n plus 1. See, we have got e to the power a delta t, therefore this error we can actually write e to the power alpha t plus delta t into e to the power I km x divided by e to the power a t e to the power I km x is equal to e to the power a delta t. So this equation must be satisfied for stability. Mod of 1 minus 4 alpha delta t by delta x square sine square km delta x by 2 must be less than 1. All right, or in other words, this equation. I think if you can remember this equation, it will be quite good. So just remember this final equation, not the entire derivation, but you should be able to follow what has been done from the lectures. All right, so this means, what does this mean is, so see this sine squared km delta x by 2, you know, so the condition can be written to be alpha delta t by delta x square should be less than or equal to half, because this will always be less than 1. So this is the final solution that we get for stability. Very important. So you should remember this one as well and this one as well. All right. So the final solution here, alpha delta t by delta x square less than or equal to half, gives the stability requirement for which the solution of the difference will be stable and solution will proceed in stable manner if it satisfies the above relation. So which relation? This relation. Okay, that is the final solution. So the above mentioned analysis using Fourier series is called von Neumann stability analysis. So you must be in principle knowing what is von Neumann stability analysis. So using this we are actually going to, until the concepts which we have learned till now, we are going to solve this one question using this now. Okay. So the question is, classify the steady two-dimensional velocity potential equation, which is 1 minus m square phi xx plus phi yy is equal to 0 when m is less than 1, and secondly when m is greater than 1, and third when m is equal to 0. So like always we are going to use the white screen for this. Okay. So solution 2. All right. So first we write down what is given to us: 1 minus m square into phi xx plus phi yy is equal to 0. All right. So therefore A is equal to 1 minus m square. So you remember that we said discriminant of b square minus 4ac we have to calculate. You remember that part? Okay. Here there is no b, but c is equal to 1. All right. So I'll let me take you to that, because that is quite important thing to see. A f x x plus b f x y plus c f y y plus d f x plus e f y plus f f is equal to g. So let me just quickly here. So you see our equation, right? It is, I'll write down here. So it is 1 minus m square f x x, instead of f x x we write f phi x x, plus there is no phi xy, so 0 into phi xy, plus c is 1 into phi yy we have, plus there is no only f phi x, so we just write 0 into phi x plus 0 into phi y plus 0 into phi is equal to 0. That is the, so when we write down what we say, A is 1 minus m square and b is 0, okay, and c is 1, because only these three terms are being used in the discriminant. Because so you see the classification depends on b square minus 4ac, right? Good. So see, we have to classify the steady two-dimensional velocity potential. All right. Very good. So I think it would be better if we start doing this problem in our next class, because otherwise this is a slightly long problem and needs little bit more detail to solve. So I think I'll end the class today here, and we start with the solution of this question in our next lecture. Thank you so much.